Hi everyone. So we're continuing off where we left last time. So we saw the idea of the GCD, and here given two integers a and b, one divides both of them, so the GCD is bigger than or equal to 1. And if a and b are both positive, so the GCD of a and b is less than the maximum of both. So one idea is that we could try to see all possible linear combination of a given a and b. So how I imagine that is that we consider, so let's write that as a remark. So if we consider a and b and we consider all the possible linear combination of a and b, then for those specific a and b, we can see that we start with a, we move it a certain amount of steps by x, and then we add to that certain amount of steps of b multiplied by y. So the total steps of both that are given by a and b, what goes into those steps is actually the greatest common factor of both a and b. So let's see this idea and try to analyze it carefully. So given integers a, so let's see a couple of analysis first. So given integers a and b, we could just consider the following set ax plus by, where x and y are elements of z. So how I imagine that is, I imagine that you're taking a, increasing it or decreasing it by a certain amount of steps, and same thing with b, and we're adding the total steps to each other. So in particular, what is the minimum amount of steps in the positive direction that we can take for both a and b? So that would be the factor that can go the highest into both a and b, because that captures both steps of a and b, and that enumerates all the possible jumps of a and b. So you could say, for instance, let's see. Yeah, so let's analyze it with first, let's look at a is 2 and b is 4. So in that case, the GCD is 2. But if we take 2x plus 4y, so then we can see that all the possible jumps of 4x, of 2x and 4y can be captured by the GCD of a and b, which is 2, because that would be, for instance, that would be 6. So all the possible evens, right? Yeah. So let's look at something which is a little bit more complicated. So let's take a to be 18 and b to be 15. Then the GCD between a and b is equal to 3. And so what about if we take all the possible jumps of A and B. So you consider AX plus BY. So that would be 18x plus 15y. So because we can see that all of these jumps are reached by the highest common factor of both A and B, so that generates all, so the greatest common factor of A and B generates all that set that could be generated by the addition of 18x and 15y, where x and y are integers. Because while other factors would generate certain jumps, it doesn't generate the whole set. So you can try it out with elements. I suggest it. So let's see. So that the main proof relies on that idea. So let's start with writing again theorem 1.2 and proving it. So what theorem 1.2 says is that given two fixed integers a and b, you can write the greatest common factor as a linear combination of both. So that makes sense because the greatest common factor captures any steps of the linear combination of both A and B in the most optimized fashion. So let A and B be integers, not both 0. And let D be their greatest common divisor. And then there exist not necessarily unique integers U and V such that D is a linear combination of both. So the main idea relies on what I've mentioned, is that you consider the all possible linear combinations of B and N and of A and B. Then you find out that the least positive element of that is the greatest common divisor, and that would mean all other elements are multiple of that. Yeah. So let S be the set of all linear combination of A and B. So S is equal to AM plus BN such that M and N belongs to Z. So first of all, we notice the following. Let D be the GCD of A and B. And then if y is equal to a m plus bn, then we can write d as a factor of both a and b. So that means that we can write d times alpha 1 is a plus d times alpha 2 is b. So that means that d alpha 1m plus alpha 2n, so therefore d divides y. So as you can see here, what any element inside of S is actually a multiple of d. So that means that d is always a factor. So what I will show here is that the minimal element, the minimal positive element of S is actually d. So what is that? That's very interesting because it tells you that d generates the whole set S. So first we show that S has positive elements to invoke the well-ordering axiom. So simply take m to be equal to a and n is equal to b, then a squared plus b squared is a times a plus b times b, which is in S, and moreover a squared plus b squared is bigger than or equal to 0. And we have that since both are not 0, then that means that a squared plus b squared must be positive. So since a and b are not both 0, so that means that a squared plus b squared must be positive. So therefore S contains positive integers, so therefore S contains positive integers and hence must contain the smallest positive integer by the well-ordering axiom, and hence must contain a minimal by well-ordering axiom. Call it T. So, by the definition of F, the definition of S, we have that T is equal to AU plus BV for some integer u and v. So we first show that this t is a divisor of both a and b. So we do that. So first, step 1, we show that t divides A and T divides B. So we will do that by the division algorithm and the well-ordering axiom. So by the division algorithm, we can divide A by T. And there exists integers Q and R such that A is T multiplied by Q plus R, where R is between 0 and T. So that means that we have that R is equal to A minus T times Q. So let's write, we can express T as a linear combination of A and B, so AU plus BV times Q, which is A minus A times Q times U minus BV times Q. So that means we can write that as A multiplied by 1 minus QU plus B multiplied by minus V times Q. So as we can see that R is also a linear combination of A and B. So that means that R must also be in S. But by the choice that T is the least positive element inside of S, so that means that R must be 0, because that would contradict the axiom of choice. The axiom, not the axiom of choice, the axiom of the well-ordering axiom. So here, R must be equal to, therefore R must be equal to 0. So therefore A is a multiple of T. So therefore T divides A, and by an analogous argument, by a similar argument, T divides B. So T is a common divisor of both A and B. So let's show that it is the greatest common divisor. So next we show step 2 is that if C divides A and C divides B, then C is less than T. Okay, so we know that T is the least element of the least positive element of the linear combination of A and B. So we have A plus B times V. So we have that C divides A and C divides B. So that means there is two integers, K and S, such that C multiplied by K is A and C multiplied by S is B. So that means if you factor C, we can see that C divides T. C divides T, so therefore, C divides T, so therefore C is less than or equal to T. So this shows that T is the greatest common factor. Greatest common factor of A and B. So again, let's analyze what's going on. So as I've mentioned here, D is a factor of both A and B, and it is a factor that generates all the possible elements of the linear combination of A and B. So we have seen that if D is the greatest common factor, then D divides the elements that are generated by that set S, and it is actually the least, we've shown that it is the least positive element, so it generates its most optimized, it is like, the way I see it, is the most optimized number from A and B. So that's essentially what it means to be the greatest common factor anyways, because it's a factor of both A and B, and it is the greatest such one. So I'll end the video here, and next time I will go on and see more things that we can prove about properties that seem to be useful in number theory. Thank you.